Hi guys, welcome to Mathematical Modeling, M447. This is just going to be a brief introduction to the subject. Let's see. Well, the main thing to know about mathematical modeling is we never try to model anything exactly. Oh, let me get my highlighter here. Yeah. We're always doing simplified versions of reality. We're never trying to capture reality in its full complexity. So that means we have to choose which features of reality are most important to us for whatever our purposes are. And as some examples, you could think of games as a kind of mathematical model of reality, right? Very often games are based on economics or war or real estate. Like Monopoly or there are other real estate games besides Monopoly. But when you make a game based on a real world situation, you always just try to single out the parts of the real world that are fun, right? And you kind of neglect the parts that are tedious or even unpleasant. So games are in a sense a real good example of this approach of modeling reality by very carefully selecting just some aspects of the reality that you want to model, right? I'll do an example on the next slide. Another example, one of the early examples we'll do is population growth. We'll do what's called stratified population models. In any kind of mathematical model of population growth, well, by the way, you probably did one already in calculus, right? You probably did exponential growth, right? Exponential growth and exponential decay. So exponential growth of population, exponential decay of chemicals or radioactive material. And that's a really simple model because it just takes into account what the current population is and basically nothing else, right? So in the exponential population growth, the rate of growth is determined solely by what the current population level is. You can imagine doing much more complicated models where you have you take into account, well, for starters, you might take into account how many men, how many women, or animals, males and females. You might take into account genetic groups, right? There might be some genetic groups that are more likely to reproduce than others. You might take into account fitness, right? Genetic fitness in the Darwinian sense. There are all sorts of things you could take into account. So if you really look at the population in its full depth, then every individual is different, and in order to study population growth or any other aspect of a population, you'd have to have a model of each individual, right? So of course that's really impractical. So all models of population growth will simplify things. As I said, the exponential population growth model tends to only look at the current population level, but we can look in slightly more depth at the layers of the population, the cohorts in the population. So for example, what we're going to do in our stratified population models is we will look at age cohorts, that is groups of individuals of a certain age, and because that age is closely correlated to their population growth, right? So for example, sexually immature individuals are not able to reproduce at all. Young individuals reproduce very quickly, and then as you get older and older, the reproduction level tends to fall off, right? And that's true for most animals, right? So by looking at levels of population in all these different age groups, we can get a more accurate idea of how the population will grow. Nevertheless, it's an extremely simplified model right, of the population as a whole. But it might be good enough for whatever your purposes are, right? If you're raising, I don't know, if you're raising horses or sheep or something, maybe that model is adequate for your purposes. Another example, this is quite topical right now, is the epidemiological, or the category of epidemiological models, modeling disease spread. So, typically, the classic starting point for modeling disease spread is the SIR model. And we're also dealing, of course, with a population of many individuals, but in this case, we're looking at it with respect to the spread of some disease. And so the relevant categories that we would want to break the population down into would be those who are susceptible to the disease, those who are currently infected, and those who have recovered or no longer infectious. And you can imagine breaking this down even further. So, for example, in the infected category, you might want to break infected down further into those who are infected but asymptomatic, right? Asymptomatic. You might have want to consider those who are infectious versus uninfectious, right? So as we've seen with the coronavirus, it's possible to be infected but be asymptomatic, right? It's also possible to be infected and be not yet be infectious. So there might be a latent period when you're not yet infectious. And so you might want to break this category of people who are infected by the disease down into further subcategories to get a better idea of the progress of the disease. Nevertheless, even with a simple SIR model, you can get some realistic results about how a disease would spread under various assumptions, right? And this is one we might do later. Maybe this lends itself in particular to computer modeling, which we'll do in the last unit. But again, there's all sorts of complexities in the real world that you could conceivably take into account, like how what are they called? Comorbidities, right? Like the SIR model ignores. So the SIR model ignores things like comorbidities. Ignores things like comorbidities. That is, what pre-existing conditions, comorbidities, pre-existing conditions you might have that make it more likely that you'll come down with a serious or dangerous case of the disease, right? That your symptoms will be dangerous. It ignores things like prior immunity. So there's some speculation with the coronavirus that it may be that if you've had a similar virus in the past, you might actually have some immunity to the coronavirus. And although actually this would be easy enough to model in the SIR model. We would just say that people who have prior immunity, we could start them off in the recovered category. We could say that they're essentially already in the category of people who have recovered from the disease, in the sense that they're not going to be susceptible to it in the future. Anyway, there are all sorts of things that you could take into account. You could take into account genetic predispositions and things like that. But the SIR model only takes into account three variables, three categories, and nevertheless it gets some reasonably realistic looking results. And you can use, for example, the SIR model to estimate the number of people who must be immune in order to have herd immunity, right? Which I'm sure you've heard a lot about lately. Let's see, another category of things. Oh, business, yeah. Business and economics, that's a big customer for mathematical modeling. In a sense, economics is all about mathematical modeling of this extremely complicated system of international commerce, right? And there's absolutely no way you can model every detail of it. So they tend to look at just a limited number of things, like the total, GDP of a country, and they do not, as far as I know, maybe now with supercomputers they're starting to do it, but they don't look at every single product that a nation produces and every single factory and things like that, right? So you have to limit the number of variables you're going to look at. Also in business, in a sense, business, for an individual business, it's a simpler problem because you're only trying to maximize the profit of your particular company. You're not interested in the economy as a whole. Even there, you have to do quite a bit of simplifying because you typically will want to look at only a limited number of categories of customers. Customers who buy high-end products, customers who buy low-end products, customers who feel loyalty to your brand, casual customers, customers who maybe are skeptical of your brand, right? So you'd only have a limited number of categories. So in all of these cases, you see how we have to limit the aspects of the real world that we're actually going to take on in our model. Right? Now let's see. Now another thing worth pointing out is mathematical modeling typically makes heavy use of probability theory. And probability theory, in a sense, is intrinsically a model of the real world. As far as I know, let me see, there are very few things, maybe with the possible exception of quantum mechanics, where they claim that basic quantum phenomena are essentially random. With that exception, I don't think anything in the natural world really follows a pure mathematical probability distribution. Right? For example, one thing that's common if you've had a class like finite or a class in elementary probability theory, you probably were taught about the notion of equally likely outcomes, right? Like, for example, if you flip a fair coin, then both heads or tails are equally likely. If you roll a fair die, all 6 numbers on the die are equally likely to come up. In the real world, that essentially never happens, right? Outcomes are almost never equally likely. I think experiments have been done with coins where they flipped a coin like 1,000 times and found that they actually do. There's a slight bias towards either heads or tails, presumably based on, I don't know, aerodynamics or the weight distribution on which is slightly different on different sides of the coin. But anyway, in the real world, outcomes are never equally likely, and a lot of probability is kind of based on that. Another example, in the binomial distribution, when you repeat a series of trials to create a Bernoulli process, for example, when you're flipping the same coin over and over again and you count the number of heads that you get, it's seldom the case that the trials are really independent of one another, right, in the real world. Coin flipping comes pretty close, I think, to trials being independent, but even then you might have subtle effects, like maybe if you got heads one time, you might actually flip it a little different. Maybe if you got heads several times in a row, for example, you might actually want to try flipping it a little differently, a little more energetically, or something, in order to get a different effect. You might do that subconsciously, right? So there are all sorts of effects like that, which might be subconscious or difficult to trace. I mean, another kind of silly example would be if you roll a die. In principle, it's going to suffer a certain amount of damage in being rolled on a table for hundreds of times. So in principle, after you've rolled it a couple hundred times, it may no longer have the same probabilities that it had originally. So for all these reasons, the notion of independent trials is kind of artificial. Another example, the normal distribution. I'm sure if you had any course on probability, they talked about the bell-shaped curve and the normal distribution. Well, the normal distribution, in a sense, arises as a limit of the binomial distribution as n goes to infinity. And in that case, well, of course, in our world, nothing ever really goes to infinity, right? We deal with finite objects, and we can never do anything an infinite number of times. We can never repeat a trial an infinite number of times. So this is already a fiction, right? This idea of taking a limit as some quantity goes to infinity. And so the normal distribution is really an idealization of the binomial distribution. I mean, that's one way of looking at it. It's a kind of idealization of the binomial distribution where you pass from the discrete distribution. Remember, the binomial distribution deals with a random variable that can only take integral values, right? And so it could take the values from 0, 1, 2, 3 up to some n, but it can't take non-integral values. It can't take fractional values. The normal distribution kind of generalizes the binomial distribution and makes it into a distribution on the real numbers, right? So that the normal distribution can take any real value in principle. And for that reason, it's actually nicer to work with in many cases than the binomial distribution. The binomial distribution, let's see, you may remember this. Let me make a note over here. The binomial distribution has two parameters. It has n, the number of trials, and it has p, which is the number of the probability of success in a single trial. The normal distribution also has two parameters, mu and n, and sigma, I should say, sigma. So the mean and the standard deviation. Although you can get most of the results that you need from the normal distribution by just working with the standard normal, in which there are no parameters. The standard normal is when the mean is 0 and the standard deviation is 1. And in fact, you can kind of recover almost everything you need from the normal distribution and even the binomial distribution just by working with the standard normal. So this is the standard normal. Right? It's the normal distribution with mean 1 and standard deviation, with mean 0 and standard deviation 1. So in that sense, the normal distribution, the bell-shaped curve, is a simplification of the binomial distribution because you have a single bell-shaped curve from which you can kind of reconstruct all the different binomial distributions to a certain degree of accuracy. However, the normal distribution is kind of an abstraction. It's unlikely that anything in the real world really obeys the normal distribution. Okay, one other category I want to talk about is a category of simplification when we're making mathematical models is this notion of continuous versus discrete. Okay? So in the real world, things tend to be discrete, right? We have a discrete number of people, right? You can have 10 people, you can have 13 people, but you can't have 12 and a half people, right? That's what I mean by discrete. Whereas in mathematics, things tend to be continuous, right? If you learn calculus, it's essential that the variables be continuous and that the functions be functions of continuous variables. So we have kind of a conflict here, right? The real world tends to be discrete and the mathematical world tends to be continuous. So typically, what we do in mathematical modeling is we take aspects of the real world which were discrete and we make them continuous in the model, right? So typical example, population, right, that we already mentioned. Population in reality has to be a discrete, an integral number, but when we model it, we tend to model it as a continuous variable that can take any real value. That's not a big deal because, you know, we can always round off our continuous value to get the nearest whole number. That doesn't seem to vitiate the model. You know, essentially, the model is still useful. Nevertheless, it is a departure from reality. It's interesting to note that the reason we do this, we model many things that are discrete in the real world as continuous variables in mathematics is because the continuous variables, although in a sense they're more abstract, and as mathematics tends to be rather abstract, it leads to a simplification. So continuous functions, in a sense, behave more simply and are easier to work with than discrete functions. Now, one exception to this is that time in the real world, I think it is natural to think of time in the real world as being a continuous variable, right? Or at least, time can be subdivided so finely that we tend not to think of time as being discrete. Nevertheless, very often, especially if we're doing computer simulations, it is very convenient in computer simulations to recast time as a discrete variable, right? So what we think of, although we think of time in the real world as being continuous, in doing a computer simulation, it's useful to think of it as or recast it as a discrete variable where you move from in increments of time, right? Like you move in increments of 1 second or 1 minute or 1 day, depending on what it is you're modeling, right? And that's typical of computer simulation as a whole, because computers are essentially discrete. That is, computers basically know 0 and 1, right? Everything in a computer is based on the numbers 0 and 1. And all the real numbers, all the decimal, the floating decimals that you get when you ask it for the square root of a number or something, it's really all based on discrete calculations. So there's a sense in which whenever you do a computer simulation, any variables which were continuous in the real world must be modeled as discrete variables in the computer. And that's just a necessary aspect, an inevitable aspect of doing a computer simulation. So, okay, so these are all ways in which we have to simplify the real world in order to create mathematical models that are useful, right? We might be able to create models that are extremely accurate, but they'd be so hard to calculate with that they'd be useless, right? So we want the model to be simple enough that we can calculate various aspects of it and various aspects of its solutions and its progress in the future without sacrificing so many aspects of the real world that the model becomes so detached from it that it's not useful for predictions, right? So a mathematical model could be useless for two very different reasons. It might be so unrealistic that it doesn't capture any part of the real world, or if it captures too much of the real world, it might be so complicated that it's impossible to compute with, right? So those are two opposite ways a model could be useless. Okay, here I want to talk about the stock market game, or a stock market game. There are many of them. In this one is called Railways and Robber Barons, or just 1830 for short. So it's about the coming of railways to Britain in around 1830. And what you do is you play a tycoon who buys and sells railroads, railroad lines, and lays track and buys engines and that kind of thing. I just want to talk about the aspect of the game that involves modeling the stock market. Oh, by the way, if you're interested in the game, this is it. It's 1830 Railways and Robber Barons. You can look it up on BoardGameGeek.com if you're interested. If you like board games, this is kind of a classic. So, okay. In the game, we want to model the behavior of the stock market. But, of course, the stock market is so incredibly complicated, nobody really understands what's going to happen in the stock market. So when we say we're going to model it in a game, we're just going to model a couple aspects, just enough to kind of make it fun, right? So the only two aspects of reality that they try to model in the game is let's see, on the one hand we have the aspect of supply and demand. That is, when a stock is bought, its price goes up, and when a stock is sold, its price goes down. So we want to model that aspect of it. And the other thing we're going to model is dividends. So the stock can pay dividends. The company owner can decide to pay dividends on his stocks at certain intervals. He gets to make the decision whether to pay dividends or not, and the stock price responds to that. So typically, if dividends are paid, that means the value of the stock will go up, and if dividends are not paid, then the value of the stock will go down, because it kind of reflects the value of owning the stock. You might also describe these two aspects of the stock price kind of correspond to, on the one hand, we have, let's say, a subjective opinion. That is, how does the market feel about the stock? Is the market optimistic about a stock, or is it pessimistic about a stock? Right? And so that kind of corresponds to the supply and demand, right? Whether people are buying or selling the stock. And on the other hand, the dividends, in a sense, correspond to the objective value of the stock. If the stock is paying dividends, that means there's a concrete and short-term return on your investment, right? I mean, if you think the stock is going to pay dividends in the future, then buying it means you're going to actually make money from the dividends. And that's a more concrete value that the stock can have than just the speculative value that you think the price may go up in the future, right? So it's kind of the difference between the subjective value of the stock and the objective value of the stock, although that's oversimplifying it, of course. Okay, now the way the game models these two things is by representing the stock prices on a two-dimensional table, as you see over here. So the main thing is that these system of cells that we have here. So really, just this part of the graph. That's the one I'm interested in. That's where the game models stock prices. So the way this works is when a company owner initially starts selling stock in his company in order to raise money to buy engines and to lay track and that kind of thing, they pick one of these cells in the red box here, right? They pick one of those cells, and they initially set the price of the stock there. From that point on, however, the future values of the stock are determined by what happens within the game. So if a share of the stock is bought, then we move from a given cell to the cell above it. So you move upwards. In this case, let me see. Let's see. So for supply and demand, let's see. Maybe I need another color here. How about this? For some supply and demand, when you go, when a stock is bought, you go up, and when a stock is sold, you go down. So if for example, you're in this cell here, and the initial price is 76, if after making that initial offering, somebody buys the stock, then the price will go up to 82. On the other hand, if the first thing someone does is immediately sell the stock, then the price goes down to 71. Right? Now, the other thing you can do is you can pay dividends, right? So the company may decide to pay dividends. And the way that's modeled is you move left or right in the table here. So if after the initial offering, after setting up the initial stock offering at $76 per share, the company immediately pays dividends on the stock, then the price moves to the right, goes up to 82. And if the company fails to pay dividends at its first opportunity, then instead the price will fall to 71. Now, this is maybe not a great example of the differences between dividends and supply and demand, because in this case both things have the exact same effect on the stock price, right? Paying dividends raised the price to 82, just as buying the stock did, and not paying dividends lowered the price to 71, just as selling the stock did. However, that's not true everywhere. So you can see more generally. Let me take another example. Let's see. How about, like take a look at this square here, right? Suppose you're currently at that square. If somebody buys the stock, then the price goes up to 142. So let's see. So if somebody buys the stock, it goes up to 142. Whereas if somebody, or if the company decides to pay dividends, the stock price goes up to 140. So in this case, the the effect of supply and demand is stronger than the effect of paying dividends, right? And that's similarly in the other direction. If the company fails to pay dividends, then the price goes down to 111, whereas if somebody sells a share of the stock, the price goes down to 110. So again, the effect of supply and demand is stronger than the effect of paying or not paying dividends, right? So the game designers were trying to model this idea that although selling or paying dividends and buying the stock both have positive effects, that one may have a stronger effect in certain contexts than the other, right? So they were trying to model that in this table. And I don't know enough about business to say whether this was a good model or not, but it was effective, and that the game, by all reports, is quite a bit of fun. I haven't played it. I've only played it a couple times, but it is a pretty good game. So I think they were successful in at least capturing the fun aspects of the stock market in this game. And that was all they were trying to do. Right? In general, if you look over the table, it seems like supply and demand does tend to be more important overall, but there are exceptions in different parts of the table. So it's a rather subtle effect, whether which one is more important than the other. It depends on the context. Okay, now I'd like to do the example of the utility curve. And if you've had econ or even business, I'm sure you've heard of this, utility function and the law of diminishing returns. The basic idea is that you've got some good, so we're going to let Q represent the quantity of some good that we have, and then we'll let U be the happiness or utility that good brings you, right? So utility is supposed to be kind of a generalization of happiness. And of course, this involves a huge mathematical idealization here. Happiness is a complicated thing. You can be happy in lots of different ways. Different goods can bring you different kinds of happiness, and the same good can bring you different kinds of happiness in different contexts. But nevertheless, we're making a huge simplification here for the purpose of the model, and we're just going to represent happiness or utility as a real number, right? So we have Q, the quantity of some good, and U being the quantity of happiness that good brings you. Let's see. There are two natural. First of all, let me just make a general comment. If you're thinking about the relationship between the quantity of some good that you consume and the amount of happiness or utility it brings you, we expect that it's going to be a kind of a decreasing curve, right? That is, we expect that it'll always be increasing. Sorry, I didn't mean decreasing. What I meant was concave down. That is, it'll be a constantly increasing function. However, the increase will become less over time, so that the second derivative is negative while the first derivative is always positive, right? So it's a positive slope, but concave down function. And the reason for that is that you figure that the more of the good you have, right, the more of the good you have, the happier you're going to be. But the more of the good you've already enjoyed, the less difference it's going to make to your happiness, right? So when you've already gotten, for example, if you win the lottery, right, and you win, it's been reported that you won $2 million in the lottery, and that's going to make you very happy. But if next week you win another $2 million, it probably won't make you as happy as the first $2 million did, right? Because you've already won. You've already enjoyed a lot of money, and the second $2 million is not going to mean as much to you as the first $2 million did, right? You're becoming a little jaded, or you're experiencing the law of diminishing returns. So we normally expect that utility curves, that is the relationship between utility and the quantity of some good that you've consumed, it's going to have a shape roughly like this. Now, there are a couple natural ways you could achieve this. There are two very simple and obvious ways you could model the law of diminishing returns. First of all, let me just point out, we're going to assume, for the purpose of mathematical modeling, that utility is actually a function of Q, and in fact that it's differentiable. And that's kind of a bit of a leap, maybe, but there's no reason to think that whatever the neurological functions are in your head that produce happiness as a result of consuming some good, like eating donuts or pizza or something. There's no reason to think that function is really differentiable, but it's a reasonable, again, it's a mathematical abstraction or idealization that we allow in order to model this mathematically. And it's not too unrealistic because we do know that differentiable functions are quite flexible. You can approximate any function with a differentiable function, right? So even if the true function, such as it might be, isn't differentiable, we nevertheless imagine that we could approximate it pretty well with a differentiable function. So we're not giving too much up with that assumption. Okay, now, in that context then, one way to model the law of diminishing returns is to look at the derivative du dq. How does the rate at which utility increases with respect to q differ at various points along this curve over here, along this graph? Right? So one way to do it is to say that it's inversely proportional to the amount of utility you've already derived from this good, right? So the rate of increase in utility with respect to the good that you're consuming is inversely proportional to the amount of utility you've already gotten, right? So if something has already made you very happy, then getting some more of it isn't going to make you that much happier, right? The basic idea. But another very natural way to do this would be to say, again, look at the same derivative, the rate at which utility is increasing with respect to the quantity of the good. But we could say that it's inversely proportional to the amount of the good that's been consumed. Right? So notice that the difference is, it's whether we're taking whether we're saying the rate of increase of utility is inversely proportional to the utility itself or to the good itself. Now, utility is kind of an abstract concept. It's kind of an intangible thing. So this is kind of a way that you might want to measure the law of diminishing, or model the law of diminishing returns when you're dealing with intangible goods that don't have a kind of a natural measurement in themselves, or a natural way of measuring the goodness in themselves. So, for example, I'm thinking that something like just money, right? People tend to be happier when they have a lot of money in the bank, when their net worth is high. And billionaires, they kind of compete with one another, even though they've already got more money than they could possibly spend in several lifetimes. They still, they like to play one-upmanship with other billionaires, and it makes them happier to know that they're richer than the other guy. But they don't get anything very concrete out of the money. It's just bragging rights, right? So I would suggest in a case like that, when you've already got enough money for all your needs, then this might be a good model for how utility works. Right? That is, we would expect that your future increase in utility would be inversely proportional to the amount of happiness you already have, right? The amount of utility you've already derived from all that money. On the other hand, there are some goods that obviously have a very concrete impact on your life, like food and shelter, and transportation, air conditioning, things like that have very concrete effects on you here and now. And those are the kinds of things that you might appropriately model with the second differential equation. So I'm thinking this might be appropriate for concrete goods, right, where you can really measure concretely, quantitatively, how much of a good you have and how much of a difference it's making in your life, right? So this would be my suggestion, that we could use these two different mathematical models for slightly different contexts. Now, if you solve these differential equations, which you can do easily using the separation of variables method that you've probably learned in Calc 2, right? Both of these can be solved easily using that method. In the first case, you find that the solution is u is proportional to the square root of q. Right? So k is just a constant, just as c was a constant up here. Right? So k is just a constant, so u is proportional to the square root of q. In the second case, we find that u is proportional to the log of q. Now, by the way, this is usually taken as the utility function. This is kind of the classic utility function where u is proportional to the log of q. Now, the difference between the two is that the log function decreases much more slowly. Right? Now, actually, let me use a different color here. So let me use green for the classic log function. Now, the classic log function is 0 when q equals 1, and it's negative when q is less than 1, so it looks something like this. But then it tapers off much more slowly than the other one. So using purple for this one, right, for the square root function is going to look more like this purple curve. So that's like the square root function, and the other one is like the log function. And so what happens with the log function is that it decreases more slowly, right? An interesting thing here is that if you apply this to the question of taxes, right? That's kind of a natural way to imply it. You might think that, for example, when we tax people, what we really want to do is kind of remove a certain amount of their utility. Right? That is, people have a lot of utility, might be willing to part with some of it, but we don't want to take utility if it's going to really affect their basic happiness. Right? We don't want to take away people who are living a subsistence life, right? Just barely getting by. We don't want to tax them very much because they don't have much utility to spare, right? So you might think that a good way to look at taxation would be to think about utility. And if you think about it that way, I won't go through the details. You can ask me about it if you're interested. But if you think about it that way, in the first case, for intangible goods, it would suggest that taxes should be at a flat rate. That everybody should be taxed the same percentage of their income, actually, that it gives them the same. Then the utility charge to each person would be the same percentage. Whereas if you look at it in terms of the second one, this would suggest a kind of a progressive taxation rate, where we tax poor people less, a smaller percentage of their income than we tax rich people. And this kind of, I would suggest that this kind of explains the difference in political attitudes between the two classes. It seems like the rich as a class tend to prefer a flat tax, whereas the poor and even the middle class in general tend to prefer a progressive tax. Right? And this might explain that. I don't know. I'm just throwing that out there. Okay, let me do one last example. This is from the days when I was a geeky high school student. I don't know if you guys have ever seen this. Have you ever seen cassette recorders or cassette tapes? You've probably seen them in movies. Maybe your grandparents have a cassette player or something. But there used to be a little a spool of magnetic tape that would play, and the tape would unwind from one spool to the other, and the tape ran at a particular rate of speed, and the tape ran over a magnetic head, so there was a head that read the tape. Let me see if I can do this. So there was like a head here that read the tape, and then it would read off electrical impulses and play music. It was amazing. This is in the days before digital, right? They had to do things with mechanical systems like this. So anyway, I had this question. Well, typically a cassette player would have a meter, a little meter that would tell you how many times one of the capstans, one of these spools, would have rotated, right? So it would tell you how many times that had revolved, right? So n was the number of revolutions of one of those capstans, right? And that number would be displayed. And then what I always found frustrating was that there was no easy way to tell how much time had elapsed on the tape, and therefore how much time was left on the tape. So I wanted a way, as I said, I was a real geek in high school, I wanted a way to relate the number n that you could see. It was displayed in a window, right? You could see this number n. I wanted to relate that to the time elapsed on the tape, right? The amount of time that the tape had been playing, right? Okay, so what you can do to solve this question is you can make a simple kind of model of the cassette tape. So what I did was I said, well, in reality, of course, the tape is actually wound in a spiral pattern, right? So the tape is actually a spiral pattern. However, for the purpose of modeling this, what I did was I assumed that the tape was actually formed concentric circles around the capstan, right, rather than a spiral. Because if you think of it forming concentric circles, then it's easier to work with the volume of the tape and the amount of tape, right? Easier to measure the amount of tape that way. So okay, so I made a model of the cassette tape in that way, and then I was able to get an equation that relates the n and t. So the way it worked was this: we assume that w is the width. So w is this width. It's the width of each layer of tape, right? N would actually then be, it would not only be the number of revolutions, so this would be w, the width of each tape, but n would also therefore tell you how many layers there were in the tape, right? Because the number of revolutions would correspond to the number of times the tape had looped over itself, so it would count the number of layers. And therefore, on the one hand, we can say that the area of the tape, so if you measure the area, let's see. And so here we go, yeah. So if we measure the area of this tape here, the area of that tape on the one hand would be equal to, well, you know, we just take the area of the big circle minus the area of the capstan in the center. So the area of the tape would be basically, oh, I forgot to subtract something, didn't I? I should have said, yeah, I should have said this minus pi r squared. Right? So subtract off the area of the capstan inside. And then what happens is, and then on the other hand, the area of the tape we can also get by taking into account the speed of the tape. As I said, the tape has to move at a constant speed, s, say, inches per second. Right? The tape has to move at a constant speed over the head so that it can be read properly and translated into music. And so if s is the speed of the tape, then you can also calculate the area of the tape by simply saying it's s times w, the width of the tape, times t, and that would be the total area. So setting these two together, if we set, on the one hand, the area is SWT, and on the other hand, it's equal to pi times r plus nw squared minus pi r squared, then what you find ultimately is that time is going to be equal to some quadratic function of n, right? And let's see, yeah, it's going to be, and I should have said this, minus pi r squared. Right? Okay. So in any event, what it boils down to is that time is a quadratic function of n, right? T and n are related by a quadratic function of n. So, you know, once you've got that, then you can set about trying to figure out what these constants are in the quadratic function. Right? So you can try to figure out what a, b, and c are. And in that way, you can then, and by the way, you can do this experimentally. If you've had a course in statistics, One way to do this is to do some linear regression and try to figure out what these constants. I guess technically you might say this is quadratic regression, but basically you do regression to figure out what the best constants are here. In any event, that in principle solves the problem of how you relate the time and the number of revolutions, right? By making a model of the cassette tape, the simplified model of the cassette tape, in which the tape is layered in circles rather than in a spiral, right? It simplifies reality a little bit, but not so much that we don't get useful results. And in fact, this was pretty useful. It was fairly accurate.